Hey guys, this is going to be part one of the AP circuit notes. And this is going to deal a lot with Ohm's law. Ohm's law is going to tell us that a current is directly proportional to the voltage drop across it, independently of the value of the voltage drop. So our resistance doesn't change. This is a digital multimeter. We're going to use this to measure all sorts of different things in here, whether it's voltage, current, or resistance. An ammeter is going to be something that measures current. You're going to have that in line in your circuit. It actually has to be part of your circuit for it to be measured. A voltmeter is going to measure a voltage drop from two different positions in your circuit. And an ohm meter is going to measure resistance. An ammeter and a voltmeter, you'll have to have a closed circuit to measure the voltage drop or the current. For an ohm meter, you have to have an open circuit. So you don't want to have a closed circuit for that. Voltage is measured across things. There's going to be a voltage drop, a loss of the pressure from one side to the other of a component. And you can see the ports that it's in. For current, we're going to have to switch this to this port, and the current will actually go through the meter. The straight lines on here tell us that it's DC. The squiggly lines, the sine curve, tells us that these up here are AC. And here we can see, if we trace the path of conventional current, it actually has to go into there and go down, and you can see that the port actually changed. Hello. So in this picture, our ammeter is going to be this one. So we have current coming out of this battery. It goes through the light bulb, and it goes into this meter and goes back. So this is our ammeter, whereas this one is just measuring the voltage drop from one side of the light bulb to the other. So that's our voltmeter. Here's the values that they get in the lab, and you guys will be doing this lab. So this is measuring a voltage drop of 2.49 volts from one side of the light bulb to the other. Our current is 98.8. This is milliamps. So it's really 98.8 times 10 to the negative third amperes, or 0.0988 amperes. All right, so what would this look like if I were to draw it? If I were to draw it, I have the positive side going to the light bulb. Then it goes through an ammeter, and then it goes back to the negative side. And my voltmeter is across the light bulb itself. All right, we'll do this in person. All right, so batteries are going to be stored energy. You'll be looking at the video of Volta and Galvani and how this was discovered. But this is the late 1700s, very early 1800s when we first did batteries like this. Prior to that, they were like the Leyden jar I showed you. So you got a certain amount of energy out of them, but it pretty much was gone immediately. So what Volta discovered was that if you had different types of metals and then an acid, that we could have this chemical reaction, and it seemingly lasted forever. Now, we know that batteries don't really last forever, but if you compare it to the Leyden jar where it just discharged and then that was done, the fact that you could pile these metals on top of each other, and that's what we did, instead of just having two metals with the acid in between it. He did it over and over again, like the electric ray we'll see in the video. And we have one type of metal that would like to attract electrons and one that would like to get rid of electrons. So how much this wants to move is a measure of voltage. So a battery doesn't supply electrons. Anything that you would hook a battery up to is already full of electrons, and they're already moving in there. They're just not moving in any ordered way. So what you're providing with the battery is a purpose, a direction to flow. So we think about this in terms of a water analogy when we talk about electricity. And in the water analogy, the battery is the pump. So if you've ever seen a pump in a pool, a pump doesn't fill up a pool. It doesn't add water to the pool. It moves the water that's already there in one direction. And that's what the battery does. How much it pushes is a measure of its voltage. So a 9-volt battery is going to push more than a 1.5 volt, and plugging something into the wall is going to push it even more. So a battery stores chemical energy that's turned into electrical energy. And you can put the batteries end to end to increase how much it pushes. Now it's going to keep on going until those metals disintegrate. And really, we get rid of batteries way before that even happens. So if you're in your calculator, if you were to measure, like the 1.5 volt batteries are almost 1.6 volts when you get them. By the time you take them out and your calculator won't work anymore, they're probably like 1.3. And so you don't have enough to get it to flow. So if they go in one direction, that's DC current. If they go back and forth, that's oscillating current. In your home, you have oscillating current, and the same electrons vibrate back and forth 60 times per second. So it's 60 hertz. If you put something in the path of the battery from one side to the other, we make a circuit. And so the idea is that we put things in the way and the current will flow. In reality, we know that it's the electrons that are moving, and we agree that it's the flow of positive charge when we talk about problems. There's no discernible difference in any of our calculations whether we took the negative to flow or the positive to flow. Keep in mind, the fact that electrons are negative and protons are positive is completely arbitrary. It just happened to be that the thing that Ben Franklin described as positive ended up being protons, and the thing that Ben Franklin described as negative ended up being electrons. And remember, the explanation was one of bookkeeping, of accounting. So we in physics problems always talk about the flow of conventional current. A convention is something that we agree upon. We have a bunch of conventions, so we can all study physics in the same way. The definition of current is charge over time. If you remember, we have our base units. We had kilograms, meters, and seconds, and everything that we learned so far was a combination of those three. In the last section, we had a new one, which was coulombs. And so now our current is going to be how many coulombs we have per second. This new unit is going to be an ampere, named after Rene Ampere. So a current of 3 amperes is measured in a circuit how many electrons pass any given point in a second. So our formula is I equals Q over T. I can be uppercase or lowercase, very much like Q can and M can. And so Q is going to be equal to I times T. So this is going to be 3 amperes times 1 second, or 3 coulombs. And then remember, a coulomb is a ton of charge. And so we know that 1 electron's charge magnitude is 1.6 times 10 to the negative 19th coulombs, or 1.602 times 10 to the negative 19th coulombs. And we get 1.9 times 10 to the 19th electrons. We can connect batteries end to end. When we do, we just add the voltage together. So each one of these is 1.5. So if I put them in series like this, I have 1.5 plus 1.5 plus 1.5, or 4.5. If you put batteries opposed to each other, the bigger battery will overpower the smaller one. And so if I have a 20-volt battery and a 12-volt battery here, I'm going to end up with the equivalent of an 8-volt battery. This might seem unusual to do, but you guys do it daily. This is how we charge any kind of battery, is putting something in a circuit backwards and forcing the current to run in the opposite direction. Batteries are often known as EMFs. This goes back to Faraday. This stands for electromotive forces. And this is how Faraday described what was going on. I'm not a big fan of this because it's not a force, it's a potential. Forces have units of newtons, and this does not. This has a unit of volts. In parallel, you don't increase the voltage, but you get more current. When I was your age, I worked at a marina, and we had forklifts that lifted boats and stacked them 4 high. And the batteries that started a forklift are very much like car batteries. They needed to be 12 volts, but we had 2 of them. So you have 2 in parallel, so you can get more current to actually start the forklift up. The difference between electrocution and shock. Electrocution is going to be current running through something until you are dead. Shock just means that excess charge went through you to the ground. So here's somebody receiving a shock. They are providing a path for the charge to get back down to the ground. Here's a woman who is apparently touching a non-grounded hairdryer and her faucet, and she is being shocked. She says, "Yikes." Here's someone barefoot touching looks like a computer tower. And so if it isn't grounded, there could be built up charge on the outside of it. The ones that have 3 prongs, if you think about what your outlet looks like, it kind of looks like the face. The hot ones are the eyes. The mouth is the ground. So not all plugs have a ground. Not all of them, it's necessary to have a ground. If you don't have a bunch of conductors on something, you're probably not going to build up a bunch of charge. So something that's metal, where it'd be a chance where you could build up a bunch of charge on the outside of it, you would definitely want that to be grounded. And then the ground, like I told you guys before, goes to a big stake that's actually hammered into the ground, and it's based on whatever the code is. So this is somebody being shocked. He climbed this telephone pole, and the power company came out and they shut off the voltage at the lower height. But that can be done locally. The voltage at the higher height has to be done at a bigger distance. The way power lines work is the ones closest to the ground are the safest, and as you get higher and higher and higher, they're more and more dangerous. So the lowest ones around your house would be like phone lines and cable lines, and then the power that goes to you. The very highest ones are high voltage. And so there's a potential of 0 here, there's a potential of 500 volts there. This charge will flow from the high to the low, and this is a picture seconds later when he touches the high and the low. The flash made the camera go, make it look like it's dark out. And that's why birds can land on non-insulated wires. So a lot of wires, the insulation just falls off of them and they're just bare wires. And bird can be just sitting up here on it, and because it's 500 volts here and 500 volts there, there's no difference in potential across its feet. There's no reason why current would flow through the bird. And they do that because they're warm. So if current's flowing through them, then there's some heat that's associated with that. And then we know about using a jolt of electricity to stimulate a muscle, in this case, heart. So again, high volts, low current. I'll show you guys this in class as well, but very often in circuits, we'll put a sacrificial piece of metal whose whole purpose is to fail. And that's the idea of a fuse. So as current goes through things, they're going to get hotter and hotter as more and more electrons fight their way through the molecules. And so as it gets hotter and hotter, if you know what the metal is, you can design something that when the current gets to an unsafe level, it actually burns in half and breaks the connection, and then you have to replace them. So these would be like the ones in holiday lights. These are the kind that used to be in homes. This is the kind that would be like in a car. And it's just a sacrificial piece of metal that you have to replace, which is different than a circuit breaker. So a circuit breaker has a bimetallic strip. Metal expands at different rates based on what it is made of. So as this heats up, the one side bends more than the other. When enough current gets through and it gets to a certain temperature, it goes enough to get to this little notch. When it gets this little notch, it breaks the connection. So now your circuit is open. Immediately, that metal starts to cool and go back to its normal shape. And then all you have to do is forcibly reset this, which is to get this out of here. If you've ever turned on or off power in a circuit box, it's easy to turn it off if it's not flipped. It's harder to flip it back on. The reason is when it's not flipped, you're just sliding it across into there, that little groove. When it is flipped, you're trying to get it out of the groove. So you have to be very forceful to do that. We can draw circuits, and when we do, we call that a schematic. And the idea is that it's easier to not have to actually draw a battery and a light bulb. We can just use symbols for it. The symbol for a battery is two lines not touching. One's longer than the other. The longer one will be the positive one. Again, these aren't universal, so you might see that would mean the same thing to me. So would this. In some circles, this would mean you have 2 cells. This would mean you have 3 cells. As far as AP is concerned, this is just a symbol no matter how many cells you have. So our circuit's going to be a closed path. When we build these, we're going to have it be an open path to start with, and then you're going to test it by closing that path, which will be what the function of a switch is. So a switch looks like a door if you were looking down, straight down from the top, what a door would look like if it was open. And then when we close it, we're pressing that to close the switch.